With the concept of algebraic filtering in place, we will introduce the algebraic neural network architecture in this video. Algebraic neural networks are defined as a stack layer structure. Each layer consists of the algebraic signal model A sub L, M sub L, rho sub L, and the map sigma sub L that is a composition of a nonlinearity operator and a pooling operator. Like in any ASP model, the pair M sub L and rho sub L is a representation of A sub L. The mapping between layers is performed by sigma sub L. At layer L, the input x sub L minus 1 is first processed by the filter rho sub L of A sub L for the intermediate feature. Then, the intermediate feature passes through the nonlinearity and pooling operator sigma sub L to generate the output x sub L. The above operation can be represented equivalently as a nonlinear map phi of x sub L minus 1, calligraphic p sub L, calligraphic s sub L, where calligraphic S sub L is contained in the set A sub L and highlight the properties of the filters, while S sub L is the set of shifts associated to the representation pair M sub L and rho sub L. This figure shows the architecture of the algebraic neural network with three layers. At each layer, there is an algebraic signal model. We first process the input with the algebraic filter and then process the result with the nonlinearity and the pooling, and then we generate the output for the next layer. In fact, the processing at each layer can be performed by a family of filters, which leads to multiple features. To be more precise, the f sub L minus 1 inputs are processed by f sub L times f sub L minus 1 filters rho sub L of A sub L superindex GF to generate intermediate features. The latter are first aggregated over the input index G and then pass through the nonlinearity and the pooling sigma sub L to output features at layer L. Here, A sub L superindex GF is the filter processing the G feature X sub L minus 1 superindex G, and F sub L is the number of features at layer L. Note that layers may use different and specific algebraic signal models A sub L, M sub L, rho sub L. In particular, the algebras can be different, but they are usually chosen as the same. The trainable parameters are the filters A sub L superindex GF, while numerically we directly train on rho sub L of A sub L superindex FG. The pooling operation is meant to increase the computational efficiency and to improve the performance. In a general algebraic neural network, this operation is attributed to the operator sigma sub L, which is the compositions of the operators eta sub L and p sub L, where eta sub L is a pointwise nonlinearity and p sub L is a pooling operator. The only property assumed from sigma sub L is to be Lipschitz and to have 0 as a fixed point. This is sigma sub L of 0 equals 0. It is also important to point out that the pooling operator p sub L projects elements from a given vector space M sub L into another vector space M sub L plus 1. We now provide explicit examples of algebraic neural networks. We first consider traditional CNNs, in which we particularize the algebraic signal model as the typical signal model. Make the vector space M equals Cn, and A the polynomial algebra in the variable t and module t power n minus 1. And S equals C is the cyclic shift operator satisfying C to the power of k equals C to the power of k module n. Substituting above definition then yields the operation of the traditional CNN layer. In this case, the polling operator P sub L is a sampling operator, while the nonlinearity eta sub L is the ReLU function. The second example is the graph neural networks, which particularize the generic algebraic signal model to that one of graph signal processing. Let the vector space M equals Cn with the n component x sub n of the signal x in M associated with the nth graph node. Let also A be the polynomial algebra in the variable t. The homomorphism filter ρ of A is then given by the polynomial in the sheaf S. Here, S is the graph matrix representation, such as the adjacency matrix, the Laplacian matrix, and so on. Substituting these definitions, we can obtain the operation at each GNN layer.